Alrighty then, so we're going to learn about what are known as Kirchhoff's rules. And if you say it with that accent, it's kind of cool. Yeah, I said Kirchhoff's rules, also known as Kirchhoff's loop rules. So this has to do with a circuit that is a little more complex than what we have seen. So what we've seen so far is a circuit where there's basically one way for the current to flow. We're going to have these other circuits that are more complex. So this, you see how this has two batteries. And the first thing you do when you look at this is you think, well, in which way does the current flow? So it looks like the current would flow that way, right? This is the positive, this is the negative terminal of the battery. And it looks like the current would flow this way. And so when they get to this junction right here, it looks like they would kind of team up, and both of the currents would pass through this region of the circuit and then would cycle back through the batteries. So anyway, this is an example of what we will do. So you have these notes, and yeah, then we're going to do this one. And so this one, take a look. This battery, it looks like the current would go this way, right, from the positive back to the negative. And over here, the current would go this way from the positive back to the negative. So we have this region here where they're kind of going to be dueling it out. And it's like, well, does the current flow that way or does the current flow that way? So we will figure that out. All right. Rules are based on two things. One is conservation of charge and one is conservation of energy. And so when we talk about conservation of charge, we mean that electrons are not created or destroyed, and it applies to a circuit like this in that the currents add together at a junction. How do we spell junction? There we go. Currents add together at a junction, and so what this means is, for example, if we have something like this, and we have this current, we're going to call that I1, and we have this current I2, we could call this current 3, and what we could say is that current 3 equals current 1 plus current 2. So this is known as also the junction rule. So in this region where two parts of the circuit meet, it's like the electrons in have to equal the electrons out. So this is just an example of that. Let's put that off to the side. Yeah, you go away. Okay. So that's based on conservation of charge, and then conservation of energy says that, and let me get rid of that fat marker, the sum of the voltage drops around a loop has to be 0. So sum of voltage drops around a loop equals 0. So I'm going to show you some examples of these. Well, two in particular. So first, we have this situation. And when you look at that, or you're given a circuit, the first thing you want to do is think, in which way do I think the current will go? And again, we're talking about conventional current, so positive, negative. And then based on that, you want to name the currents with these variables. So I'm calling this current 1, this current 3, and then through the middle current 2. Okay, and again, current 2 here, it looks like is going to be current 1 plus current 3. So that's the junction rule, and this is our first equation. So right here, using conservation of charge, we said that current 1 plus current 3 we think is going to be equal to current 2. And I say we think just because, I mean, it will, but sometimes the current is actually going to be going in the opposite direction that we think. Not in these examples. Okay. Find the current in each part of the circuit. So we set up that. Oh yeah, and then these two equations. So these two equations are based on these two loops and the fact that the voltage has to be has to add up to 0 all the way around the circuit. So if we look at this loop, we have 9 volts, and so 9 volts is going to equal the voltage drop across this plus the voltage drop across this. And we know that V equals IR. So what I have said here is that 9 volts is equal to 25 ohms times, so resistance times current, and then plus resistance times current. So notice how we have two variables in there because the current through this part of the circuit is different from the current through this part of the circuit. So that was for this loop here, this equation. And then this loop right here was this equation. And so we say 12 volts is equal to the voltage drop across this plus voltage drop across this. Okay. So your favorite, right? Look at all this math all over the place. We have 3 equations, 3 unknowns we can solve, use our algebra skills. So I think what I did was I took this one and I said, all right, current 1 is equal to current 2 minus current 3, and basically substituted this in here so that we have 2 equations with 2 unknowns. And the idea was to get current 2 and current 3 as our variables. So we're just trying to get rid of this current 1 using this, and there will always be some simple junction rule equation that you substitute into these, and then you get 2 equations and 2 variables. So the difficult part about these is that the numbers end up being kind of messy usually, and then there's just a lot of steps and a lot of potential for mistakes. So I've solved 2 for us. Let's see. So I replaced current 1 with current 2 minus current 3, so that's right here. Distributed and then combined. So 25I2 plus 68I2, we got 93I2, and then minus 25I3. So this and this from here are now our 2 equations with 2 unknowns. So we could have substituted. I just went with the sort of add, subtract, or elimination method and multiplied. For some reason I thought that was going to be easier, and it kind of was. So I wanted these to cancel out, so I multiplied by 25 and by 35. And in the second example I'll show you a slightly different technique, because you see these numbers and you freak out, but whatever. So these cancel, we add together, we end up with this, and we get that I sub 2, so the current 2 equals 0.124 amps, and that is to the left. And I put this in here because let's take a look at our diagram. We ended up with a positive number, and we had defined this current as going this way. So if we ended up with a negative number, it would have meant that the current was flowing that way. But it's not. Okay, so you know from experience that once you get this, you can substitute into the other equations in order to find the other variables, and I think I chose the original equations from up top, plug this in, and ended up with current 1 is this, and current 3 equals this. And it turns out that our guesses as to which way the currents were flowing were correct, because these ended up being positive numbers. Okay, so that's one example, and just in summary, alright, we're using this junction rule, and then we're adding up the voltages around each loop. And from that we come up with multiple equations that we do a bunch of algebra with to end up with our answers. That's the bottom line. Let's take a look at example 2. You may try solving it by yourself, that would be fun. Or we could just take a look. So I think this is what I did, is I said that this voltage is greater than this voltage, so I was just kind of assuming that at this part, right, because this is going to be pushing current that way, whereas this is going to be pushing current that way, so we don't know who wins the pushing war, the tug of war here. But because this voltage is greater, I said, alright, let's define I sub 2 as going this way. So first we have the junction, and so right here we have current 3, current 2, And do you see how they're going to add up to be current 1? Alright, so that's at this junction. Hey. So what do we say? I1 equals I2 plus I3 at this junction. And I think we could do the same thing at this junction, and it would look the same. Well, no, I know that we could, but I'm trying to skip steps. So we have this equation for the for the currents coming into the junction, and then these we set up for the loops. So for the 5.8 volt loop, we have 5.8 volts equals voltage drop across the 120 ohm resistor plus voltage drop across the 74 ohm resistor plus voltage drop across the 56 ohm resistor. When we look at the loop for the 3 volt battery, we have 3 volts equals voltage drop across the 25, and then look at this, I have subtracted this because we defined I sub 2 as going upwards. So this would actually be a negative voltage drop here. So we subtracted that, current times resistance, and then plus current times resistance for this over here. Alright, so I think that we were looking for current 3 and current 2 to be our variables. So I have substituted in here to replace current 1 with current 2 and current 3. Look at all this math. Distribute, 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 distribute. And we get one equation involving current 2 and current 3, and another equation involving current 2 and current 3. So at this point, we have our 2 equations, 2 variables. We could substitute. In the previous example, I just said, hey, I want these to cancel out, so multiply by 250 and multiply everything by 56. But instead, I think this was a little easier. In order to get these guys to cancel out, I said, well, I could multiply everything here so that this turns into a 250, which would be 250 over 56, and that way these are both 250 and they cancel out. So they ended up being some kind of messy decimals for these two numbers, but in the end I think it was not too bad. So this works, of course. We could have substituted. We ended up with 250s here, add, divide, and ended up with current 3 is 0.026 amps. And if you're looking at the book solutions for this question, the book solutions have this as 58 volts, whereas the question in your homework is 5.8 volts, like we're solving here. So the book solutions are a typo. Alright, so we ended up with current 3, substituted in one of the original equations to find current 2. Notice how it's a really small number, which kind of makes sense. Current 2, remember, because we have current being pushed this way and current being pushed this way, so a lot of it's going to cancel out. And most of the current is going to flow sort of this way through the circuit. And then lastly, for the current 1, substitute values. Oh look, I have the current 2 plus current 3, so we end up with this. And notice also how, with these messy decimals, the problem is you have rounding errors because we multiplied, and then we're adding, and then we're dividing, so it's all these successive steps. So I tried to include a lot of decimal places within the calculation, and then do some rounding. Ideally, we'd be using significant figures for our answers. Okay, Kirchhoff's loop rules. Thanks for listening.